Hello, students. Section 5.2 homework. So I've got 1 through 4, 5 to 10, I guess 1 through 10, 13 to 22, and 24, 25, and 33. Let's take a look and see what's coming up in 5.2. That was in part A. Need to get to part B. Oh, of course. Couldn't have that. Couldn't have it all clickable. Let's see here. Oh, now we're in chapter 6. All right. Let's get back. And hopefully, there we go. So we're into the homework here, and let me jump over to, okay, here we go, 5.2b. So 1 through 10. So again, some of these use patterns to show -2 times -2 is 4. I think that should be pretty self-explanatory from the pattern pieces that we've already seen. If you haven't, just you can check out the videos. I kind of show that. Again, patterns are not my favorite approach, but it works just fine. Chip model to show the following. So I won't do that exact problem, but I think it's important that you kind of understand the chip model's probably the best model. Again, could be just my opinion, but it is easy to work with and it demonstrates the concepts pretty quickly. So you can kind of get the idea. So if you were doing, this one says -2 times -3, that's multiplication. So again, if you were doing this, if I was doing, let's say, negative, I don't know, whatever I want to do, -3 times +1. So this first number, when I see it, is telling me to take out 3 groups. Take out 3 groups of what? Of +1. So we start with 0. We can put in, I need to take out 3 groups of +1. I don't have anything right now, so I definitely need 3 groups of +1. So I'm going to make 3 groups of +1. And I'm going to also put in, so these are black and red chips, and we'll see those in class when we use them. But a black and a red together kind of make 0. Those are the 0 pairs. So this is the chip model actually with physical chips. The one shown below is the charged field model with like pluses and minuses. But again, they're very similar. There's almost no difference between them. All right, so let's take a look. So now what I have right here, this is 0. It is 0. There's nothing here because they're all 0 pairs. And it says now take out 3 groups of +1. Okay, well, here's one group of +1, one group of +1, one group. There's 3 of them. And so I'm going to take out 3 groups of +1. And then the end result becomes red, 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 which is the same thing as -3. So again, the only difference you might have is yours might say -2. So you'll take out 2 groups of whatever it is. And then over here, the +3 would be put in. So in that case, you'd be putting something in instead of taking something out. So you'd start with 0 and then you put in these groups as you're doing it here. Okay. So again, we talked about 2 different ways to see the division. So a division, if you're dividing by -6, then you want to make piles of -6 and you want to count how many there are. All right. And likewise over here, if you're dividing by +3, you could do the same thing. You could make piles of +3. But again, if you have -21, that's not going to work so well. So you could make 3 piles instead. How much is in each pile? All right. So good questions there on the chip model, something that'll definitely be showing up on an exam. I use the number line model to show this. I only put one question on there because I do want you to see different models. That doesn't necessarily mean every model is going to make it to the exam. Okay, next one. In the chip field models, the encircled charges. So this is a chip model, but it charges. So it's really the charged field model. You can see what is the multiplication problem happening here. And so again, notice if I am taking things out, then the first number I multiplied by must have been negative. And look at how much is coming out and how many groups of them. And if you think back to what we just did with the group pieces, you can kind of see, oh, I could turn this back into a multiplication problem. Let's see here. The number of students has been decreasing at the rate of 20 students so it's going down by 20 students per year. Assuming the trends continue, write a multiplication problem that describes the change in the number of sophomores taking math for each of the following situations. The change 5 years ago, the change over the next 4 years, the change in the next n years ago. So just remember, if you're decreasing, then that would be like a negative 20 students per year. And so if you're doing it over 3 years, you might say that it's 3 times negative 20. If you wanted to do 2 years ago, you might say it's 2 times the opposite. So 2 times positive 20, or you could write it as negative 20, and then you multiply by the number of years, you'd put in negative 2 years, kind of saying 2 years ago. So there's really 2 ways to think about it. Yeah, and it's kind of up to you as to your preference. Use the definition of division to find each integer quotient. Okay, so if it's not defined, explain why. So anyway, I'll leave that up to you because that's just the definition of division. Remember, it has to be a perfect multiple. Evaluate each of the following if possible. So on some of these, they're asking you maybe to simplify, right? That would be a really good thing to think about. Yep, and then you have some with numbers. So I'll let you, again, this is just doing a little bit of arithmetic. Evaluate each of the following products, and then if possible, write 2 division statements that are equivalent to the multiplication statement. So this is similar to the 4-fact families. If you have multiplication, you could write multiplication in many ways. I'll do one up here. So if we had 3 times 5, that equals 15. We also could say 5 times 3 equals 15. We could say 15 divided by 5 is equal to 3, and we could say 15 divided by 3 is equal to 5. So here's 4 facts that are kind of all linked together, and they're saying take this and turn it into a couple of division problems. Okay, so find the answer and then turn it into division problems so that you can see that going forwards and going backwards. Let's see here in the following x, y, and integers, use the definition of division to perform the operations and then write your answers in simplest form. Okay. I don't think there's too much of an issue there. Again, if you're dividing something by 5, you could think of maybe factoring that out so that you end up with like a 5 divided by 5. But I'll leave that up to you. This is very similar. Question 10 and question 5 are somewhat similar. This one is like a chemical lab. The temperature is -5 degrees. It decreases by this many degrees per minute. What will the temperature be m minutes later? So it's very similar to what you did here. It's just now you're going to be doing it with a variable. In a sense, you'll be creating an equation someone else could use to solve a problem. Let's see here, 13 through 22. Compute each of the following. So these are order of operations. If there is maybe a most commonly missed problem, it would be something like this, -3 squared. I find that a lot of times students will put this in their calculator as -3 squared like this. These are very different. And let me just describe why. In the first one, the object being squared is -3. So this would be -3 times -3, which we know to be +9. If you do -3 squared without the parentheses, the object being squared is just the 3. And so this looks like, and think about this opposite out in front here as the opposite of 3 times 3, which would be -9. So be careful about those, how you write them, as the opposite of something is different than the value itself. So there's 13. X is an integer. Which of the following expressions are always positive and which are always negative? All right, that sounds like a good always, sometimes, never type question, because something raised to the 4th power, could you say that it is always positive? Could you say that it is always negative? Could you say that it's sometimes? See here, find integer values for which these are true. So now you're actually solving these equations where you're going to put numbers in and make sure the numbers actually work out. And I said through 22, so we'll click over here. So those you could do algebra. You could do a little bit of guessing, but you want to make sure that you've got a good idea. So I would definitely push the idea of doing a little algebra as you keep going. Let's see here. 54 divided by x is an integer and x is an integer. What are the possible values of x? This goes back, it ties back together with what we did in chapter 4. So we're talking about divisors again, because it does divide. Identify the property. So remember, if you need to, flip back a few pages, but you have the identity property, commutative, associative, distributive property of multiplication over addition. Those are kind of the property names that we're looking for. The quotient of two integers is -4. Find 4 possible pairs of numbers. Oh, there's actually infinitely many pairs of numbers for this question. I just want you to find 4 different ones where you would divide them and end up with -4 as a result. Let's see here. Multiply the following and combine like terms. So again, a little bit with algebra, thinking about that idea. How do I distribute negatives? Find all integers, if any, that make the statements here true. Oh, so again, now this is not saying the statement is true or false. It's saying that the statement depends upon the numbers that I pick. So for example, if I pick up here, I say, well, if x is equal to 3, then 3 squared is equal to 9, and that'd be great. So one of my solutions that I would write is x equals 3. But is that the only number that I can square and get to 9? And remember, multiplying a number by itself is the same as squaring it. And so the other option you could get to is it could be -3, because -3 squared is +9 as well. So there's actually 2 numbers, 2 values that will make that true. Okay. You'll see a couple in here like this one that just says, hey, this thing is negative. That was very, very similar to what we had right before, which said find, are these always positive, always negative? They're kind of asking now, if it may or may not be true, can you find some numbers that do make that happen? Right, yeah, difference of squares formula. So this is a little bit of algebra, multiplying things out and then going the other direction. We've also done this, we did this back in 3.4, I think, 3.4, 3.5. And this one says factor. So again, this is the idea of going forwards and backwards, multiplying and then factoring as you do it. And the last one is show that a minus 1 squared is equal to a squared minus 2a plus 1. And that's again an algebraic formula, but it's a pretty good one. Let's see here. I went to 22. Oh, 24 through 25. Oh, I guess you didn't have to do 23. All right. Ooh, arithmetic sequences. So now find its common difference or ratio and find the nth term. Remember, common difference is for adding or arithmetic, and common ratio is for multiplying. So try to find what are they multiplying that is common, or maybe what are they adding that is common, and then see if we can't go back to what we did in chapter 1 and write a general term. Let's see here, 25. So now again, keep that thought going. And here is arithmetic or geometric. So take a moment, take a look and see what kind of a sequence is it. And then see if you can't find the missing terms by kind of expanding that sequence. And let's see, how far did I say to go? 24, 25. Okay, so that was it for that. Oh, and I think I said one more, didn't I? 33. All right, so the lowest point of Lake Superior is this. For deep, you drop a bowling ball in the lake and it travels 36 feet per second. Write the information using integers. Calculate how long before the bowling ball hits the bottom of the lake. Wow. So 1,300 feet deep is pretty big, right? You drop a bowling ball in the lake and it travels at 30. So again, think about 36 feet every second. What are we doing? You know, you're kind of trying to break up that depth into chunks of 36 feet, and your goal is to see how many of those does it take. So again, definitely using multiplication or division there. And that's it for the homework section. So let's see, is there anything here? I guess maybe I can do one of these along the way, like a 22. So again, when it says factor completely, they are saying factor until there's nothing else possible that you could factor except the number 1. So here these have an x in common. So you could bring the x out in front and that would leave behind a plus 2. And that would be completely factored because a and 2 do not have anything in common. All right. Hopefully that helps. If you have questions, let me know. Have a great rest of the day. Off you go.